Hi all. Thank you for joining here. I'm Navis from SK Telecom. And it's early in the morning here, and I feel a little exhausted staying up all night watching the great keynotes and sessions. Today, I will talk about the experience of building and running a Druid-based product for 5 years. Druid is inherently easy to expand its functionalities in diverse aspects, and I think it allowed us to do the task for that long. It's about me. I am a software engineer, started my career as a J2E implementer 20 years ago, and spent most of my time on big data projects. I am a committer of Apache Hive and member of PMC. I was a committer of Druid once, but I'm not now. Currently, I'm in charge of Druid in SK Telecom and run branch for years. Here is the agenda for today. I'll talk about what we are building with Druid and how we are reinforcing Druid for that. The rest is about some challenging issues. One thing I should confess before the start. This presentation is only about Druid itself. Here comes out no Druid cluster, no Druid tuning, no Druid best practice, and no Kafka, Flink, or Kubernetes. So if you are expecting any of them, you are probably in the wrong room. I don't know much about them. Sorry for that. Productizing Druid. To make a long story short, we want to build a BI tool that can handle big data. How did we get started on the project? As a telecom company, there is a lot of data from all over the country, but most of them were in separate expensive silos like Oracle or MS SQL. Enterprise-wide integration and consolidation project was underway, and we built a visualization tool for that. And Druid looked promising for that purpose. For 5 years, we've done quite a good job of it, I think. It's named Metatron Discovery. For anyone interested, here is the homepage address. It's not very well maintained, but I wish you could find some interesting articles in the blog section. So what can we do with Metatron Discovery? First, it has a prep tool running on a Spark cluster. Prep means data preparations. It allows you to cleanse, enrich, and validate data visually. Also, it has a data source manager. You can manage ingress, egress data, RDBS, Hive, of course. Lastly, it is a BI tool. You can explore, analyze, and visualize anything you want as you need. Okay, that's all. So why Druid? Why have I chosen Druid among others? First, it is fast, because it is driven by memory mapped I/O on a columnar format with effective filtering based on bitmaps. Fast enough to interact with user reactions, which is most crucial for building a BI tool. Second, it is versatile and adaptable, because it has an extendable module system and well-organized interfaces in codebase for internal extensions. Third, it is made of Java language, because it's what I can do best. Nowadays, there are other options, especially if you are not considering implementing your own module or functions. There is the Apache Pinot. I call it simplified version of Druid. Here, simplified means it has fewer boilerplates than Druid, not lack of functions. And ClickHouse is also worth considering, simple to use and cost efficient. But there are no other options at that time, and we haven't many complaints because we've been exploiting the extension system of Druid extensively. We've made hundreds of new functions by a dozen of new modules. Druid is good, but how far can you go even further with Druid? It is the story of today. From now, I'll show you some use cases of Metatron Discovery. All customers have their own problems, and some are impossible to solve without evolving from the innermost or Druid. The start is Telecom company or our company. In our company, SK Telecom, the first use of Metatron is for analyzing CDR. CDR means call detail record. It contains various attributes of the phone call, such as time, location, duration, status, etc. Via complex consolidation processing of data from diverse sources, we make one number called CEI. It's calculated and presented by Metatron for monitoring and optimizing the quality of phone calls. In here, Metatron successfully replaced some legacy tools like Spafire. The network operation team also uses the same cluster for operating cell coverage and managing communication facilities. Here are some screenshots. The left shows the status of network and cell coverages. The right is CEI trends that I've mentioned. So what have we done for them? It can be categorized into three parts: custom formats, Hive integrations, and geospatial features. Custom file formats, though providing connectors for notebooks like Jupyter or Apache Zeppelin, some external processes still depend on other tools like Excel, Python, and RStudios. They want to ingress or egress files into or from our Druid cluster easily. So naturally, supporting various formats is the first thing to do. Formats like OC, Parquet, Excel, multi-line CSV, JSON, even Druid segment format. Among them, supporting the Druid segment format is remarkable because it means we can make a Druid table again from the query result. That's somewhat similar to materialized view, but we call it simply a temporary table. Here, temporary means it only exists in the broker. You can make it non-temporary if you insist. In that case, the broker will push the segments into deep storage, making them permanent and visible to all. And then the coordinator will distribute them across historical nodes to serve queries. This table building can take some time depending on the amount of data. So we also provide an option to do it asynchronously. So all with these formats, we can ingest and create table from an Excel file, join it with other tables, and publish the result as Druid table or Excel file on HDFS or S3. All this process also can be done via SQL. Here is an example of creating Druid table from an Excel file. All we need is one SQL string. The long part type string is for providing schema. It's not necessary for schema providing formats like OC or Parquet or shapefile format. Types can be deduced from data, but still we need the name of columns. By running the SQL, we create temporary table from it. We can do anything possible with it as it is a usual table. Things like group by or joining with other tables. Importantly, visualizing it on screen. And eventually, we need to write query result into diverse formats, or make another table from it with the CTAS clause. The next is on Hive integration. Apache Hive has been vastly and extensively used as data warehouse in many companies for a long time. I'm not saying that because I'm involved in Hive. Batch ingestion prevails for some larger projects, and most of them were from Hive. So it was in SK Telecom. Seamless integration to Hive is substantial for the adoption of Druid. As a Hive committer, making a storage handler was the first thing that came to my mind starting the Druid project. Here is what I presented at the first Druid meetup in Seoul. The storage handler supports base functions like column projection and filter pushdown. And unofficially, it is the first SQL interface of Druid. It's fascinating. However, it had a performance issue. You can see 50 seconds took to count only 5 million of rows. It became significantly faster with a follow-up project improvements, but it couldn't make it. It's not in use currently. One more reason is that the storage and logic system in Hive was a little inconsistent from varying versions. For ease of ingestion data from Hive, I've implemented a connector for Hive Metastore. Anyone who has experience with batch ingestion spec will know that it requires quite a focus. You should provide type-of-run informations like path or schema, and the full class name of input formatter is somewhat confusing. We've simplified it to mirror Hive table name and partition specs. Then those pieces of information are automatically retrieved from Hive Metastore and populated into ingestions. It lessens the burden of users and reduces the human errors significantly. And in some departments, Hive UDF and UDAF is a standard form of user-defined function. Codes they are developed via outsourcing and distributed to multiple stakeholders. Any modification or porting is barely recommendable. So we need to call Hive functions in Druid as is. Calling stateless function like UDF is relatively easy. But for UDAF, it's very complex because of different life cycle and context. And also should stick to internal assumptions of Hive that are hard to know before reviewing source code thoroughly. Too long to explain. I should admit it's done really in a hacky way. But I can tell it's working and still used in a production environment for years. Now the hack is wrapped as a car-side SQL operator, and we can call them in SQL as well. It's part of log messages in Bootstrap. You can see Hive functions registered to Druid. Also, geospatial features are required. It seems natural because there are many GPS coordinates in data generated in Telecom company. And those are used for various purposes like navigation service or location-based target marketing. We need to store, filter, calculate, and manipulate them effectively. Druid supports R-index for handling coordinates, but since it uses a Euclidean coordinate system, GPS coordinates should be converted back and forth, entangling considerable overheads. And how can I implement those spatial functions? I don't know even it's possible. So we need an alternative approach. The idea of using Apache Lucene instead of R-index was from a seminar introducing Elasticsearch, where they are showing an early version of Elasticmap. I have some experience with Lucene to implement an index on Hive for text search, so it was not as difficult as I first presumed. This is what I presented at the fifth mirror. You can see the implementation detail on the link. With the hard working of Lucene and helpful functions borrowed from various geospatial libraries, we achieved expected behaviors. Now we can answer complex questions like show me the area in a map within the range of 10 meters around the rows, where the coverage of the communication repeater does not reach. Here is a map. I've drawn this with open layers. It's called a choropleth map. Wikipedia areas colored or patterned in proportion to a statistical variable within each area. I'm sure you've seen this kind of map before, but one thing special is that this is from the spatial join of GPS coordinates and shapes of borders. In this example, GPS coordinates are stored in WKT format and indexed with Lucene using quad tree on GeoHash. OpenLayer sends this SQL to the GeoJSON endpoint of the Druid broker. It joins the location of nursing homes with the border of barrows of New York City by spatial function st contains. You can see the CRS transform function used for OpenStreetMap, which uses web mechanical projection. It's from the GeoTools library. Then it converted into GeoJSON format. You can think of GeoJSON as a single JSON object holding rows as feature collections. OpenLayers extract features from it and draws geometries on the map. There was a GeoServer between once, but obsoleted now. This seamless process implies that the power of Druid can be unleashed in a way that has not existed before. If you prefer hexagons, you can group the location of nursing homes using Uber's H3 or GeoHex. Or you can use traditional GeoHash functions to make a rectangular grid. This slide is from my presentation for ApacheCon 2018. It's about building GIS on Druid. Maps can be drawn with other graphical libraries. We are trying Kepler-GL for map views in Metatron Discovery. Let me show one more example. Among the functions we've provided for the analytical projects, there are clustering algorithms such as k-means or deepscan. By using them, we can group data vicinity or density base and show the clusters on the map. Here is the result of them with half-sign distance measure. Outer boundaries are the convexor of points that belong to it. A convexor is a geospatial function from the JTS library. Before moving on next, let's look into one more thing. As seen before, the broker can convert the result into any format. It need not to be JSON or text type. Because Druid uses REST on HTTP, any representation is possible if a proper media type is given. One example is JFree chart module, which converts query result into chart image file. Practically, it's almost useless, but it's quite fun. Here is a simple SQL query making the net sum of quantities per line number. And the new formatter will show you a pie chart on the web browser. Next is industrial companies. Industrial companies uses Metatron for equipment health monitoring and predictive maintenance. Some use it on products and others use it on production facilities themselves for yield improvement or machine tool matching. From data emitted from various sensors on compressors, machine tools, conveyor belts, and hydraulic cylinders, we believe we can find something in it. With a specialized UI attached for this purpose, we've condensed all requirements onto spin-off project, Metatron APM. Here, APM means asset performance management, not application performance management. Metatron APM is SaaS on cloud service, and it made a good impression on small to medium-sized companies that need analytical capabilities but cannot afford the cost. Here are some screenshots showing what APM looks like. The left and bottom are health monitoring screen for compressors deployed in the factory. The upper right one is status of conveyor belts distribution center. We can organize requirements into three parts: virtual column, analytic functions, and anomaly detection. Some huge manufacturing facility generates metrics in the form of map time, size of hundreds to thousands. Possible options are to explode with each key value pair on the map or to store the whole as JSON. Neither of them looks promising. The former will make too many rows with mostly null values. The latter will impact the performance queries accessing the column. That's why a map virtual column is created. For that, I made an array time multi-value handling on dimension and double array time metric. If the index of dimension value currently accessing can be visible to array metric, it's just like using a key to obtain the corresponding value. It is what a map does. To make a room for glucose emulating that, I've introduced a virtual column to Druid. And map virtual column is the first implementation of it. More popular one, the expression virtual column, is vastly used for calculating various formulas. In addition, there is a special type of virtual column. It is automatically applied when accessing elements of an array or struct type column. I call it an implicit virtual column. For example, if there is an array column named A, we can access the first element of it with A.0. You can think of item operator in Apache CarSite. Calculating conditions for alarming or predictive maintenance requires various statistical information on long historical data. Simple stats such as mean, max, sum, average are not enough. So we provide more complex ones such as variance, percentile, skewness, kurtosis, covariance, and fast Fourier transform. Already introduced clustering algorithms like k-means and deep-scan. Forecasting algorithms like exponential smoothing or ARIMA also provided. And we support dozens of window functions like read, lag, rank, skewness, and running something with a user-defined window frame, commonly combined with grouping sets. This is one example showing what window function looks like. It's a simple learning sum for monthly revenue for each customer. It's just a random SQL that I found from Googling. It runs on Druid. In addition to threshold-based simple alarm, we wanted it to base on a model from Anomaly Detection. For that, we've introduced the AGAS library and made a Druid module with that. It runs various algorithms to time series data and scores for each algorithm. Then we can choose the most fitting one and use that for alarming purpose. Any user-made models also can be used, of course. If anyone is interested in AGAS, you can visit this address. Or you can stop by the session that will be presented by creator of it tomorrow. Here are some screenshots of using anomaly detection in Metatron. Index on numeric columns. It's not exactly a requirement, but worth considering. There are so many numeric columns and also many queries frequently filter on them. Can you optimize filters on numeric column? Inspired by the success of geoindexing, I've tried bit-slice bitmap and range histogram too. I should explain what they are and how they work, but those were deprecated because it was not beneficial to performance. So let's skip the detail. For numeric columns, vectorized processing is the right direction to go, and it's what Apache Druid is currently focusing on. There was an inquiry of whether Metatron is applicable for the security control. In short, it's about whether it can replace Splunk at a lower price. We couldn't make it, but it's still interesting to see what was required and what we've done for it. You can think of the security log as that with many dimensions, a few metrics, and some text, but to an extent of billions of rows per day commonly. Since root cause analysis is the core of security control, rolling up is generally not allowed. It results in excessive use of resources like disk or memory. Due to the massive nature of data, A simple aggregation query would require considerable server cost to attain satisfying response time. And it also needs various search schemes on text columns. How do we amend these problems? It's about text search, segment compaction, and OLAP cubing. Text columns are mostly from machine-generated log messages of firewall or gateways. In other areas, it can be SQL string used for accessing RDBMS or dictation of VOC conversations by STT. Whatever it is from, you can easily guess the bitmap index would not be much help for searching on them. So instead of wasting space for bitmaps by declaring them as dimension, I made a simple string metric and attached the Lucene index. Apache Lucene is built for this purpose exactly. All search schemes of it, like term search, wildcard search, fudge search, proximal search, and combination of them are all available to Druid. In terms of footprint, the Lucene index has successfully replaced bitmaps with a slightly smaller size. I think we can call this even. Here is a sample SQL that uses proximal search on text column. It brings top 10 rows with the highest search score. Segment compaction. The footprint of Druid segment was more than 2 times bigger than that of Splunk, and we need to decrease the gap. Less footprint means less memory, because Druid uses memory map.io. For a start, compressing text columns seemed promising. A row-based compression was unsatisfactory in compression ratio. Applying block compression has risen it to 60 to 95% with query performance. The block compression is applicable to dictionary, but is not applied in real by the concern of performance. Some filters rely on binary search on dictionary. However, it's like jumping around the blocks, inducing costly decompression every time. One more thing. Among bitmap types that Druid supports, the loading bitmap is regarded as de facto standard because it's well balanced between performance and compactness. But it becomes less effective in some extreme cases in each way. Consider a primary key style dimension. Since all values are unique, only one row ID needs to be stored. But the loading bitmap makes it to 20 bytes cause the header or something like that. So I've introduced a handful of more compact formats. For example, a continuous bitmap can use run length encoding. A small size bitmap can write IDs with delta encoding. This simple hack decreases the footprint of dimension a lot. OLAP cubing. Traditional OLAP builds a cube to answer multidimensional analytic queries swiftly. A cube is a lattice of cuboids, an aggregate dataset with a partial set of dimensions. If we pre-calculate all cuboids in advance, we can answer any questions very quickly, as a key value store does. Cuboids can be solution for heavy queries done on whole security data. Apache Kylin only tries such an attempt. It builds cuboids in the background and stores them in HBase. And it uses it for handling queries. However, I think it didn't take advantage of fast writing of HBase, but only highlighted the disadvantage of bloated storage size and slow random read. A similar attempt on Druid was made by a Chinese engineer, calling it virtual data source. It builds cuboids of interest with data source name and chooses the proper one for query in broker. It's a simple working solution, but has problems. First, it makes too many segments. Second, it's hard to synchronize between cuboids. The fundamental reason for this problem is cuboid exists as a separate segment. We can solve them at once by embedding all cuboids into a segment. So when building a Druid segment, we make cuboids all together. They share dictionaries of the base segment, and it makes them more efficient in footprint. In data nodes, a query will choose the most suitable one from them and rewrite itself accordingly. It helps per segment basis and can always fall back to base segment instead of throwing an exception. It's somewhat similar to starter index in Apache Pinot. This is dump of sample segment with 4 cuboids. If conditions are right, we can process queries with a cuboid with 3,000 rows or even smaller 400 rows instead of the base segment with 200,000 rows. You can imagine the performance boost. Here are some important use cases that didn't require anything special for Druid. It means Druid is built for them. The financials like banks or insurance companies adopted Metatron for their customer information system. As for bank, they requested a more precise type for numeric column. A new decimal type and corresponding arithmetic expressions are provided with simple statistical functions like mean, max, sum, and average. I really wish to show their use cases, intriguing things like Sankey diagram, funnel analysis, and fraud detection, but it's strictly forbidden by policy. The advertising company uses Metatron mainly for the hourly report of market execution for customers, which are done by hand before. Also, marketing department in companies use it for analyzing characteristics of target users of advertisement to explore and find a wide range of customers. From here, I'll address some challenging issues not mentioned till now. Except for the ordering on time column, Druid allows order by only for group by query. However, order by on any query type is quite a common requirement. In Excel, you can change the ordering of rows by clicking the name of a column. It also has similar data view, and everyone expects it to work the same way. Sorting is easy. Stack all the rows to an array and provide a comparator, and then mission accomplished. But aside from the performance, a problem occurs in the first part, auto memory. A smart guy can solve it by partial sorting and disk paging, but I'm not confident of implementing that without bugs. Instead, I've solved it by query partitioning. If it's possible to make partitions according to the order, we can process the whole without memory issue. The story is like this. Before processing, send meta queries to make a histogram of order by columns and convert it to partitions. We can say each of them correspond to a range filter. Then send original query attaching range filters one by one in sequence. Whose partitions are contained by columns and sorted on them for each, we can concat them to acquire totally ordered results. Though theoretically works, there are many performance issues in the early days. The cost of building a histogram and processing range filters often exceeded the process of partitioning. It's been improved gradually for years, and now I can say it's working well. We can also apply this to group by query, which expects results sorted by group by dimensions for efficient combining of partial aggregations. Not only did it free us from fear of out of memory, but it improved performance unexpectedly. So we don't need disk paging, at least in data nodes. Next is on the join query. It would be the most frequently asked question for every QA session. There are situations that pre-join or normalizing is not feasible, and we need an answer for them. Function in Druid to nearest to join query is lookup. You can replace a key with a value via mem-like data, broadcasted a priori. But there are some problems in replacing join with lookup. First, the lookup table is not on Druid. It needs separated management. Second, it allows just one key column replaced with one value column. It narrows the scope of application significantly. Third, it becomes brittle sometimes on server lifting or starting index tasks. I mean, no doubt it has become stable and improved now in Apache Druid. However, there was no alternative at that time, and I've decided to implement a join query. There are various implementation methods of join. However, since total ordering has already been there, it seemed natural to choose a sort join. Now we can join tables in Druid without single key and value restriction, supporting all kinds of join types. And also, no need to broadcast something. But it can be slow because target table should be sorted on join keys. The performance of the sorting version is highly dependent on that of total ordering. I'll describe some efforts to optimize the performance Druid cluster that uses star schema. I've implemented the hash join and broadcast join. Also did filter conversion of semi-join condition and filter propagation via Bloom filtering. All these processing branches are determined based on cardinality up to that time. When join takes place over multiple stages, all these branches are all intertwined to generate complex plans. Though not writing and served our purpose. To verify whether the join query is working well or not, we use the TPCA test. It contains a lot of joins, CTs, and subqueries. It took some time, but now all of the tests runs perfectly. That means we can replace most JSON queries with SQL, allowing access to Druid for analysts or third parties that don't know Druid. Now the join query is working in various production environments. This row capture shows how a SQL is converted to Druid JSON query via Calcite Planner. I can say it's not a good idea to write a JSON query with multiple joins by hand. As mentioned, total ordering depends on range filters. However, the range filter can be slow, from hundreds of milliseconds to a few seconds. The reason is that it should union all bitmaps in range one by one. If the cardinality is not high, it is not a big deal. But what if it becomes hundreds of thousands? The loading bitmap is fast in general, but unioning hundreds of thousands is a different problem. I've heard that latest version of loading bitmap supports fork join style operations, but it can cause other issues already running on multi-threads. Instead, I've unioned them into Java bitmap and converted it back to loading bitmap. Surprisingly, this simple tiny detour was faster, like 2 or 3 times. But we need it faster. So after dividing the dictionary values into ranges, I've unioned all bitmaps of each partition and segment. If a range filter contains any of them, we can use of the pre-built bitmap instead. It boosted the processing speed of range filter with minimal use of space. Lastly, I've introduced the new cache type only for filters. Not like query cache that serves query result, it serves bitmap for a filter. Currently, I'm trying to make bitmap operation as lazy as possible to eliminate unnecessary calculations.
Navis, we have about 5 minutes left, and we have a few questions in the
yeah, it's all
in the chat. So from Jihoon, can you elaborate more on the details of why the bitmap index did not work for numeric dimensions? One of the questions
Oh.
from Q&A, can you elaborate more on why Bitmap index didn't work for numeric dimensions?
Cause it's too many cardinality for numeric types, especially for float or double types. Integer can be possibly some advantage from Bitmap, but float or numeric float types cannot that much of advantage from it.
Gotcha. Thank you. On for the next question, were there any performance considerations you had to take into consideration for the windowing functions?
I missed the important part. It's just running on the broker, just on the broker. It's not running distributed manner. It's running solely on the broker. So it's
So the window functions.
Yeah.
So the window functions are just running on the broker.
Yes.
Okay.
It can be a problem if it's just too many rows in the broker.
Okay, so you could run into, does that happen on heap or off heap?
Sorry?
In the broker, does the windowing functions have it happen on heap or off heap in the broker?
It's just on heap.
Just on heap. Okay,
I didn't make any paging things yet.
Okay, so you could run into. Yeah, so you could run into heap overflow issues. Okay, from Jung, there are so many ideas with this presentation. What do you plan to add next?
I think I didn't think about that much of projections.
That's okay. We can always move on to Cole's question. Do temporary tables require only native Druid features, or do they use custom Druid extension?
It's embedded in Druid processing module, so it's I can say it's a Druid native thing.
Okay. And also, do you use custom Druid extensions to ingest Druid query output as a permanent table?
Yes. It is what Overload doing. We make a segment and push the to deep stories and send application to coordinator to display those.
Is that file created on the broker and then pushed out to the coordinators?
Yes, it's all made in broker.
Okay. Gotcha. Okay. Well, we're at time now. Thank you very much for coming on and talking with us. It's been an absolute delight talking with you. Do you have any final comments as we close out the session here?
Thank you for joining here.
I know everybody's asking me for me to ask the question. Are you thinking of contributing any of this to open source?
I really wish to do that, but there's some substantial difference in code base of our Druid and Apache Druid, so I think it's not feasible in short term.
Well, in the long term, we hope that you do. And thank you very much for your time here. We're absolutely delighted for your presentation here. Thank you very much.
Thank you.